Hi everyone! Today we'll be presenting our CS620 data project. Ours is titled Predictive Geospatial Analysis of UFO Sightings in Virginia. Our group project was done by Naomi, myself, Sabrina, and Correy. So, a little bit of background. Why UFOs? UFO sightings are typically reported without much context, but weather conditions, especially cloud cover, play a major role in how people perceive unusual lights or objects in the sky. Our goal was to combine UFO sighting reports with reliable meteorological data to uncover whether visibility conditions actually influence UFO reporting patterns. This topic is also personally meaningful to me. My hometown was featured on the television series Unsolved Mysteries in the 1980s for a wave of UFO sightings that gained national attention. Local authors even wrote a book titled Don't Look Up, documenting decades of unusual sightings in our area. Growing up with these stories, I've always been intrigued by how communities collectively remember and interpret mysterious events in the sky. That's what made this project so interesting, and it's a way to analyze crowdsourced reports and explore a phenomenon that continues to fascinate people who are curious about aliens and the unknown. To explore this, we merged real sighting data from the National UFO Reporting Center with daily cloud cover records retrieved through the NASA Power API. Once the data sets were cleaned and aligned, we created a predictive model to determine whether UFO sightings were more likely to occur and under what cloud conditions. Ultimately, this project demonstrates how environmental data and public observational reports can be combined to reveal new patterns, offering a data driven perspective on where and when UFO sightings are most likely to occur. Kind of like I've gone over first, here are our data sources. So we use two primary data sources. The first was the National UFO Reporting Center. This data set includes thousands of sighting reports submitted by the public, complete with timestamps, locations, descriptions, and sighting durations. For our project, we filtered these reports down to just ones located in Virginia. The second major data source was the NASA Power API, which provides historical and current environmental measurements for any geographic coordinate. Although we originally attempted to use the NOAA weather records, that data set had gaps and inconsistencies for regions and dates that we needed. NASA's API provided complete and reliable cloud cover measurements, which worked well with our UFO data, and we were also able to merge these together. I would like to point out that whenever we were working through this, we kind of got a little hung up on the NOAA data weather data, just as like a side note.
Our first step was to gather the data from the UFO database for the state of Virginia. How we did this was by using a Selenium web scraper. This gave us a table of the columns for the city, state, country, date, shape of the UFO, and other descriptive fields. This initial data set included a bit less than 3,000 data points from 617 unique city fields. And it ranged from 1945 to October of this year. After that, we cleaned this data by removing the fields we didn't need and standardizing the fields by converting the date columns to datetime objects. We use Python's GeoPy geocoder to turn the city data entries into latitudes and longitudes, with us removing the data points which did not successfully geocode. This left us with 2,700 rows, so removing around 10% of the data set. The next step was to gather the cloud cover data from the NASA Power API. This one was a bit easier than the scraper. We just send them the latitude, the longitude, and the time. And the API gives us back a value from 0% to 100%, or a null value if they don't have the data for that place and time. We then encoded the values greater than 30% as cloudy, and lower than 30% as clear skies. And then we dropped all the data points that had the null values. And that was the extent of our data gathering and pre-processing. Their final result is a data set with the features of cloud cover, temporal information, and geolocation. And so for our analysis, we first did some exploratory analysis. We saw, for example, sightings were more common during the day, during the night, and during the fall. We also plotted the sightings as a heat map to see the regions where the sightings were the most common. As you can see from the map, it roughly resembles the shape of Virginia with the hotspots in more populous areas. And then for our predictive modeling, we use Python's sklearn to run a random forest classifier to predict the sky's condition at the time of the sighting. The model evaluation had an accuracy of 0.86. And then we created scatter plots of the sightings versus predicted sky conditions.
In this section, we present the key findings from our analysis exploring the relationship between UFO sightings and weather conditions. First, we found that clear skies play a major role. UFO sightings are significantly more common during clear sky conditions based on cloud cover classifications. We also identified temporal patterns. Certain months and even certain days of the week show noticeably higher levels of reported UFO activity. Geospatial hotspots emerged across the state. Sightings tended to cluster in specific regions, which became particularly evident in our heat maps and scatter plots. Our predictive modeling also performed well. A random forest classifier accurately predicted sky condition, clear versus cloudy, using temporal and geospatial features such as the date, month, latitude, and longitude. Additionally, the project highlighted several data quality challenges. Some UFO sightings lacked corresponding cloud cover data, underscoring the importance of complete weather records and robust handling of missing data. Finally, visualizations played a key role in understanding these patterns. Maps and plots made temporal and spatial trends easy to interpret. While the results are promising, the project faced several limitations. The first challenge was data availability. Our original goal using NOAA weather data wasn't feasible due to incomplete coverage. As a result, we switched to NASA's Power API, which provided more consistent cloud cover data, but with limited historical depth. There were also temporal and spatial gaps. Some sightings didn't have matching cloud cover information, which reduced the size of our usable dataset. And because the NASA API only covers certain location and dates, our predictions were limited to those specific conditions. Time constraints added another hurdle. With more time, we could have incorporated additional modeling approaches or performed deeper text analysis on the descriptions of the UFO sightings. Looking ahead, there are many opportunities for improvement. Expanding the dataset to include more weather variables, such as temperature, visibility, and wind, could strengthen the predictive power. Natural language analysis of UFO descriptions or shapes could introduce richer features. Forecasting future sightings using time series models like Prophet is another promising direction. And lastly, building an interactive dashboard would enable live exploration of sightings alongside predicted sky conditions. To conclude, this project successfully merged UFO sighting reports with cloud cover data to explore the role of sky conditions. We built a random forest model that effectively predicts whether skies were clear or cloudy based on time and location-based features. Our visualizations, such as scatter plots and heat maps, revealed distinct patterns in sightings across time and geographic regions. Overall, the findings support the idea that UFO sightings are more frequently reported during clear sky conditions. More broadly, this project demonstrates the value of combining multiple datasets for predictive modeling and geospatial analysis. It also sets the stage for future enhancements, including text-based analysis of UFO reports and forecasting models to predict future sighting patterns.